Something that we didn't mention that's also going to affect reaction rates are just simply the nature of the reactants. Like, what are they? Unstable bonds tend to break more easily versus stable bonds. If they were stable, they'd stay together. Because they're unstable, they break more easily. Like, the reactants don't want to be where they are. Also, the type of reactants. Ionic reactants usually are faster reacting at room temperature, and covalent reactants usually are a little bit slower reacting at room temperature. If we think about ionic compounds like sodium chloride, it's a great example of an ionic compound. If we place salt in water, it's going to break apart into the ions and react pretty quickly. A covalent reactant, maybe like glucose or sugar, is going to be a little bit slower to react versus the table salt. Also, homogeneous reactions versus heterogeneous reactions. Hopefully, we remember that homogeneous means the same throughout. They're all in the same phase, like maybe all gases. Versus heterogeneous reactions where the reactants are in different phases, maybe like solids and liquids mixed together. The homogeneous reactions are going to occur faster versus the heterogeneous reactants that are going to occur a little bit slower. Something else that we didn't mention is the surface area. If we look at the two diagrams, and this mostly is going to be talking about solids reacting, in the first diagram, we see it's just a big glob, like maybe a sugar cube. And the second diagram, that solid has broken apart, maybe like granules of sugar. So if you put a sugar cube, if you've ever seen that, into like coffee, it's going to take a little bit longer to dissolve versus the sugar granules, which are going to take less time. Because the more surface area, that's going to equal more frequent collisions. And this is mostly a factor for our heterogeneous reactions, meaning like solids with liquids or gases with liquids, and reactions occurring between solids. So the next factor is temperature. We discussed that the faster moving particles are going to have more frequent collisions because they're moving faster and they have more time to hit each other. Also, the faster particles are going to have more energetic collisions. We discussed that particles need enough energy when they collide with each other in order for a reaction to occur. Raising the temperature increases the rate for almost all chemical reactions. For many reactions, a 10 degrees Celsius increase in temperature almost doubles the reaction rate. And then conversely, if we're taking away heat, the particles start to move slower and they're going to have less collisions with each other and less energy when they collide. So a lot less reactions. If we were to remove heat, all of these reactions would go down or decrease. The next factor that's affecting reaction rate is concentration of the reactants. Higher concentration equals more frequent collisions because there's smaller distances between the particles. If we look at the two diagrams at the bottom, on the left you see that there's a low concentration and more space between the particles. In comparison on the right, there's a lot less space, so they're kind of just going to be bouncing into each other and having more reactions over time. An increase in the concentration of one or more reactants usually, but not always, increases the rate of reaction. For gases, increasing the pressure, which someone mentioned, also lowers the volume and increases the concentration. So we'll only see pressure affecting gases' reaction rate. Otherwise, pressure doesn't really have much effect upon reaction rate. And the final factor that can affect reaction rate are catalysts. We discussed that catalysts are substances that speed up a chemical reaction without it being permanently altered. They're not part of the reaction at all. Why catalysts speed up a reaction is because they lower the activation energy of one or more elementary steps in a reaction mechanism. And they could also allow for a different reaction pathway to occur. Like they're getting to the same destination, just taking a different route. Catalysts don't appear in the actual reaction. When we look at the enthalpy graphs down here at the bottom, the original reaction is shown in blue, and then the red is showing once a catalyst is applied. And we see a significant decrease in that activation energy. The activated complex came down, it has much less energy, so this is going to move much faster. The complete opposite of a catalyst would be an inhibitor. An inhibitor is a substance that slows down a chemical reaction. Measure the reaction rates. A rate, just like if you're driving in your car, a rate is a change per unit of time. And it's going to be the change in concentration over a change in time. We hopefully remember what concentration is, that it's molarity, your moles per liter. And generally the unit of time is going to be seconds because these reactions are occurring quickly. Reaction rate is the rate at which reactants are turned into products. And it's going to be expressed as concentration. Concentration is that capital M molarity, and that's our moles over liters of the reactants consumed or the products formed in a given amount of time. As I mentioned, the time is usually seconds because reactions are happening quite quickly. When using reactants, the rate is going to be expressed as a negative to show that the concentration of those reactants is decreasing. The units for the reaction rate are going to be the molarity over seconds. If I say meters, I really mean molarity. I'll try not to say meters. So we have that capital M over the seconds, which is the same as moles over liters times seconds. So that's where this moles over liters is coming from because that's what molarity is. Please also copy the average rate of reaction. I don't believe I really gave you room for that, where it's the change in the concentration are those brackets, over the change in time. Our rate laws are going to be an equation that relates reaction rate and concentration of the reactants. In our equilibrium expressions, we had reactants over products, and this time we're only going to be looking at the reactants. The rates kind of look similar to equilibrium though. Our expression is going to be that rate equals K. K is a specific rate constant of the reaction, and then we're going to multiply that by the concentrations, and we'll raise them to a specific exponent. We're going to determine the exponents based upon data, and we'll do that in a moment. The reactant order is the value of the exponent applied to the reactant concentration. The reactant order must be determined experimentally. And the higher order reactants have a greater effect on the reaction rate because their concentration is going to be like squared or tripled or to the third power. Orders are usually integers, but they might be fractions or even negative. And when we add all of the exponents together, that equals something called the overall reaction order. We're going to calculate our rate laws using something called the initial rates method. The concentration of one reactant is doubled, usually, in successive trials, while all other reactants are held constant and the rate is measured. If the reactant concentration is doubled, the rates will vary as an exponent of 2 in those trials. So as we look at that chart, and make sure that you're able to read these headings, I know it might be kind of blacked out, but this first column is talking about the rate, and then we have the order, because, and the new rate. If the rate remains the same, the order is 0 because we know 2 to the 0 is equal to 1, or any value to the 0 power is going to just be the same. If we double the rate, the order is 1 because 2 to the first power is 2 times the old rate. If the rate quadruples, the order is second because 2 to the second equals 4, or 4 times the old rate. And if the rate octuples, it's going to be third order because 2 to the third is going to equal 8. Third order is very rare. It's practically non-existent. And we're going to do practice with this. We're going to see what this means. So let's go ahead and calculate a rate law based upon some data. So we have this data table. You'll notice that there's 4 trials and we're only talking about the reactants, not about the product. So the rate law is specifically about the reactants. I want to figure out how the concentration of A changes. And what I'm looking for between the trials is the concentration of A changes, but the concentration of everything else stays the same. So from 1 to 2, I see that A changes and everything else stays the same. So I'm going to compare 2 to 1. I did 2 over 1 because the concentration in trial 2 is higher than the concentration in trial 1. So I'm going to write the concentration of 2 over the concentration of 1, and I'll divide them. That's a factor of 2. And I'm going to compare the rates in the exact same order, 2 over 1. The rates are in this column over to the right. The rate of 2 is 5 times 10 to the negative 4th, and the rate of 1 is 2.5 times 10 to the negative 4th. I notice that they'll just cancel out, and 5 divided by 2.5 is 2. So what I'm thinking about is this 2 to what power equals 2? 1. So the order of A is to the first order. I'm going to do the same thing for B. I want to see which trial B changes, but everything else stays the same. I noticed that from 2 to 3, B changes, but so does A. So I can't use from 2 to 3. Maybe from 1 to 3, it changes, and everything else stays the same. So I'm going to compare 1 and 3. I'm going to put whichever concentration is higher on the top. So I'm going to do 3 over 1. The concentration at 3 is 0.01, and the concentration at 1 is 0.005. So again, times a factor of 2. I'm going to compare the rates in the exact same way. So the rate at 3 is 1 times 10 to the negative 3, and at 1 was 2.5 times 10 to the negative 4. So when I divide that, that's going to be 4. So once again, I'm thinking 2 to what power equals 4? So B is an order of 2. Do the same thing for C on your own. Okay, hopefully your work relates to mine. For C, I noticed that from 3 to 4, the concentration of C is changing and A and B are staying the same. So I did 4 over 3 because the concentration at trial 4 is higher versus 3. So I compared my rates in the same way, but that's 1. So 2 to what power is 1? 0. So my order for C is 0. So my order for A was 1, for B was 2, and for C was 0. So if I wrote my rate law, I'm going to say rate equals K times the concentration of A. Since it's to the first power, that's implied. I don't have to write that. B is squared. And because Z is to the 0 order, I'm not going to include that in my rate expression because it's just 1. So that's part of what you're always going to do is write the rate expression. Now, let's use that rate expression with any of the trials. It doesn't matter. We're going to solve for K. I always just use trial 1, and I'm going to plug in to that expression. At trial 1, the rate is 2.5 times 10 to the negative 4, and my units are molarity per second. I don't know K, that's what I'm solving for. The concentration of A is this 0.001, and concentration is that capital M. And then my concentration of B is that 0.005, also M. That one has to get squared though because I figured out the order for B is to the second power. First, I'm going to multiply on the right-hand side. I'll do 0.001 times 0.005, but don't forget to square that 0.005. It's a really small number. It's 2.5 times 10 to the negative 8th. When I multiply M Okay, when I multiply m times m squared, I'm saying m squared because of this squared here. What does that become? M to what power? Cubed. And I still have my rate on the other side. Next, I'm going to just divide by that 2.5 times 10 to the negative 8th on both sides. My rate comes out to be 1 times 10 to the 4th, but let's figure out the units. I had molarity per second divided by molarity cubed. If I were to multiply the top, that's just molarity, and on the bottom I have seconds times molarity cubed. What would my final units become? What do I do with these exponents of the m's? Subtract. So 1 minus 3 is what? So m to the negative 2 and seconds to the negative 1. So this is the value for k, and you need to have the units as well. We'll do another one that's like this. Are we good with this one? Wherever you have some room, let's try another one. So let's try to find the order for A first. And you don't have to go in order of the reactants. I just like to start with A and then B and then see if there's a C. So the only time that I see the concentration of A changing, or not the only time, I see it changing from 2 to 3, but B is also changing from 2 to 3. So from 1 to 3, it's changing, and B is staying the same. So those are the only ones we can compare for A. So I need to compare 1 and 3. I'm always going to put whichever one is the higher concentration on top. So I'll put 1 on the top divided by 3 on the bottom. So 0.720 divided by 0.360, which comes out to what? 2. And then I'm also going to compare the rates in the exact same order. I'm going to have 1 over 3. So the rate of 1 was 0.470, and the rate of 3 is 0.117. And I'll divide those as well. Which comes out to about 4, like not exactly 4, but close enough. So what we're thinking about is 2 to what power equals 4. And that's the order for A. Let's do B. I see that B changes in a couple different places. It does change from 1 to 2, and A stays the same from 1 to 2. Should I do 1 over 2 or 2 over 1? The concentration in 2 is 0.720, and the concentration in 1 is 0.180. So that comes out to 4. And I'm going to compare my rates in the exact same order. The rate of 2 is 1.88, and the rate of 1 is 0.47. So 4 to what power equals 4? So the order of B is 1. So I'm going to determine the order of with respect to each reactant, which I did. A is going to be second order, B is going to be first order. What's the overall order? And my rate equals K times the concentration of A to the second power and B to the first power. I don't have to write the 1, it's inferred. Let's also find the value of the rate constant, or K. I'm going to use that expression that I just created, and it doesn't matter which trial I use, I just always use the first trial, and I'm going to plug in what I know. In the first trial, I know the rate is 0.470. The way that it's written here, the units are kind of funky. It's the same as M over S, or concentration over S. I don't know K, that's what I'm solving for. The concentration of A in the first trial is 0.720. molarity squared times 0.180 m. I'll first multiply my concentrations. Make sure you're squaring the 0.72. I really just like to keep that value in my calculator so I don't have any intermittent rounding, but I'm writing it out so that we can figure out the units. If I had m squared times m, what's the exponent? M cubed. On the other side, I still have the 0.470 m over seconds. And then I'll divide the 0.47 by what my answer was in the calculator. K equals 5.0. And that's it, just 5.0. Now for my units, I had molarity over seconds, and I was dividing by molarity cubed. So what are my final units? M negative 2, S negative 1. Same units as the last question. Okay, so what we just did was called the initial rates method. We were given information. If we're not given different trials, different concentrations, different rates, it's going to be called an elementary reaction. It's a process that occurs in just a single event or a step. And reagents are the same as reactants, must possess a minimum amount of energy to interact or to react with each other. Molecularity of a reaction means the number of molecules that are reactants in an elementary step. If it's unimolecular, like una implies, it's a single molecule that acts as a reactant. If it's bimolecular, it's a collision of two molecules as reactants. And if it's termolecular, it's a simultaneous collision of three molecules, which is very rare. So anything with just one molecule is a single molecule, unimolecular, bimolecular is 2, termolecular is 3. And you kind of see that diagram at the right if it's able to be read from your packet. If a reaction is elementary, its rate law is based directly on its molecularity. Unimolecular is first order, meaning just raised to the first power. The rate is directly proportional to the concentration of just that one reactant. Bimolecular, the elementary reactions are always second order. Doubling one reactant doubles the collisions of that reactant with the other, doubling the rate. You could see some examples of this at the bottom. So if our only reactant was A to our products, then the rate is just going to be K times the concentration of A. If we have two of the exact same reactants reacting, that's really the same as 2A, and so it kind of makes sense that our rate is going to be A squared, similar to how we wrote those equilibrium expressions, taking the coefficient up as an exponent. It could be two different reactants that are reacting with each other, and hence we wouldn't square it, we would just multiply them by each other. So if you're not given data like in a chart, you're going to look at the coefficients of the reactants, and they'll become exponents in your rate law. We also have something called a rate determining step, which is the slowest step in the mechanism. The slowest step in a multi-step reaction governs the overall rate. It can only go as fast as the slowest step. You'll generally be told what the slowest step is. As we look at this example here, step 1 is told to be the slowest step, and hence that's our rate determining step. But we also have something called intermediates. Intermediates are the same on both sides of the reaction. So as I look at this example here, I notice that NO2 is on the product side here and the reactant side. So it's going to be considered an intermediate. I also notice that NO3 is on the product side here and the reactant side here. So that's also an intermediate. Everything that's not circled, you can see kind of adds down to the bottom. Because the slowest step is our rate determining step, I'm only interested in the concentration of NO2 because that's here in my rate determining step. I didn't include the intermediate. And the reason I raised it to the second power is because I have two NO2s that I started with. So first of all, what's my rate determining step? 1, 2, or 3? Why 2? It says slow. It's my slowest step. It's my rate determining step. So because it says slow, step 2 is the rate determining step. Then I also want to figure out any intermediates, kind of like those spectator ions that we had previously. Anything that's exactly the same on the reaction side and the product side, I'm going to circle them. I see that I have an NO2 on the right here and on the left here, so they like cancel each other out. Then I notice that I have an NO2 on the right here and on the left here. I think that's it for intermediates. Nothing else that's exactly the same on the left and the right. So then I'm going to kind of add down. I have 2 NOs. I have 2 H2s. That's it on the reactant side. And then I have an N2 and 2 H2Os. So that's my balanced equation for the overall reaction. Are there any intermediates? Yeah, definitely. Everything that I circled is an intermediate. So I have N2O2 and N2O. I also want to try to write the rate law. That's going to be based upon the slowest step. So if I'm just looking at that, I have N2O2 and I have H2. However, one of those is an intermediate. Which of those is an intermediate? N2O2, so I'm just going to cross that off. That's not going to be part of the rate determining step because it's an intermediate. When I look at my balanced equation, I have 2 H2s, so I'm going to raise that to the second power. And here's my final rate expression.